Let's take a bit more of a deep dive of that. And so for that, I'd like to welcome Stefan Jensen, the Managing Director from Scantec. Stefan has quite a long and extinguished career within the refrigeration world, starting in 1978 with Danfoss in Denmark. In 1996, moved out to, was in Australia to kick off Scantec Refrigeration Technologies. Anyone in the refrigeration space is aware of Stefan. He's authored many different technical papers, sat on various different committees and what have you, and done many different presentations. So it's an absolute pleasure to have Stefan here today and telling us what's happening with heat recovery and refrigeration. So over to you, Stefan. Yep, that's come through. Perfect. Thanks, Stefan.
Thanks very much, Jared, and good afternoon, everyone, for taking the time to attend this little webinar. I'm not going to get into a lot of detail. I'll just show you a couple of heat recovery examples from our practical life, the things we do all day, every day. So here goes, if I can get this to work. Here we go. So two examples. One example is from an existing installation that was commissioned about 10 years ago. The two package chillers, water chillers, that's are air conditioning a public administration building south of Brisbane. And the chillers are using refrigerant ammonia, and there's a little desuperheater fitted to these chillers for the purpose of producing hot water, domestic water. And the other one is a very large plant. It's a 500,000 cubic metre cold store where we've fitted a desuperheater to the discharge pipe, the common discharge pipe, out of the ammonia compressors to recover some high-grade heat there that's used for a number of purposes in the plant. Now, first of all, might sort of dwell a little bit on what a desuperheater is. So this little diagram here, that round thing with a top hat is a compressor, and the other rectangular thing there is a desuperheater. I've shown this as a shell and tube. It doesn't have to be that way. The numbers 1, 2, 3, 4, you see later, they are representative of the condition of the refrigerant. So inlet condition to the compressor is number 1. Saturated suction temperature, you can see here 0 degrees. The enthalpy is shown. Once the gas has been compressed, it reaches condition 2. You can see the temperature's gone up to 91 degrees and the enthalpy has increased. Then condition 3 is downstream of the desuperheater. There we have taken the superheat of the ammonia gas out, or any gas. So that is the process that happens in the desuperheater. We desuperheat the refrigerant gas coming out of the refrigeration compressor to a point that is close enough to the saturation point. In other words, just before the refrigerant starts to condense. So in refrigeration, we use a tool that is called the lock pH diagram. Some of you will be familiar with that. I've drawn the process there, 1, 2, and 3. So 1 to 2 is the compression, 2 to 3 is the desuperheating process, and from 3 to 4 is the condensation, where we remove all the heat from the refrigerant gas and return it from vapor into liquid. Now, it's important to note here that in an ammonia plant, we can only recover roughly 12% of the entire condenser heat rejection. This is assuming we have reciprocating compressors. If we have other types of compressors like screw compressors, that 12% is less. More about that later. But here's what I've tried to show with that little formula down the bottom. In this particular case, we can recover high-grade heat to the tune of 12% of the total condenser heat rejection that comes out of that compressor, or it can be multiple compressors that operate in parallel. So here's a little photo of the first example. These are 2 water chillers, 600 kilowatts cooling capacity each. They produce chilled water, standard air conditioning temperatures from 12 down to 6 degrees. You can't quite see the desuperheater here. It's just a little silver thing that sits on top of the compressor. I don't know whether you can see my cursor on the other end, but it's sort of it's a little thing about 1 meter long by about 100 millimeters diameter, sitting right there above the compressor. And it desuperheats the discharge gas and produces about 70 kilowatts. And that 70 kilowatts can be used for heating domestic hot water. Now, there's a lot more to a desuperheating system than just the desuperheater and just the heat exchanger itself. The heat exchanger itself, you can see there in the top of the picture, that's the same rectangle we looked at before, but this time around I've added a bypass because sometimes these things, they fail, and then you've still got to be able to run the plant, the refrigeration plant, while you're repairing the desuperheater. So it's good practice to put a bypass around it. The other rectangle to the right in the picture, that is the water-cooled condenser. And then you see down the bottom here, we have another heat exchanger, and that heat exchanger sits between the water we actually consume, the water that comes out of the taps, and the closed circuit, the closed water circuit that we circulate between that heat exchanger and the desuperheater. We are required to have a double heat exchange for domestic hot water services, but I mean, we also need to have that water-to-water heat exchanger that you can see there. That's the one, if you can see my cursor, this rectangle here, because if we were to put domestic hot water or potable water directly through the desuperheater, we get formation of calcium oxide. And this happens very rapidly within a few months. And if you cannot clean the desuperheater on the water side, you can cut it out and throw it away unless you have an indirect circuit like that. Now, in calculation terms, if we know the mass flow of refrigerant, this is what is called M in that equation, and we know the enthalpy differences. This is from the previous picture. We can estimate here that we can recover about 70 kilowatts maximum out of this desuperheater. So I reduced that by 2 kilowatts for a couple of reasons. First of all, the pump costs a bit of power, and also the desuperheater has a pressure drop. And when we cause a pressure drop in the discharge line of the compressor, we increase the power on the refrigeration compressor marginally. So these couple of kilowatts, they account for those losses. I do concede that we have a gain on the condenser. In other words, the condenser that sits downstream of the desuperheater doesn't quite have to work as hard, but I've sort of ignored that in this comparison. Then we come to the, this is a bespoke ammonia plant that runs a 500,000 cubic metre cold store in Queensland. So we have a mixture of compressors here. On the left, you can see some screw compressors, and on the right, you see some reciprocators. We are recovering heat from the reciprocating compressors. They sit on the second compression stage. Screw compressors, they sit on the first compression stage. And here you see the desuperheater is of the plate type, and you can see both heat exchangers here. The blue one is the one that is an ammonia water heat exchanger, and the other one next to it, that little water-to-water heat exchanger, is the one I showed in the previous diagram. This is to create a closed water loop for the desuperheater itself, so we avoid that it fouls up. The pump in the foreground is that pump that circulates the water through the closed circuit. So again here, the plate heat exchanger you see in that picture was probably $20,000, but the capital cost of the entire system, if we include the 7.5 cubic metre insulated water storage tank that serves as a buffer, and all the other auxiliaries around it, the price climbs to about 120,000 to 150,000, depending on the extent of the pipe work and so on. So the heat exchanger itself is kind of a small thing in the scheme of things. In this particular case, we use the hot water for three things. We heat the subfloor below the freezer. This is a freezer floor that's about 240 by 120, 110 metres in that order, 26,000 square metres. So the design capacity is about 16 watts per square metre, but that's not what the floor uses. When the freezer runs at about -20, it uses between 1 and 2 watts per square metre, but we design for 16 for a number of reasons that I won't get into here. Secondly, we use the warm water that comes out from the desuperheater. It's in the order of the usual part, generally about 80 degrees. 90 degrees or 93 degrees, as you see there on the picture, is when we're running 35 degrees condensing temperature. We try not to do that, of course, because it uses too much energy. So we let the condensing temperature float, and then the available temperature from the desuperheater floats down with it. So in all the glycol air coolers for the medium temperature services, we have a little heat exchanger so that we can run warm glycol defrost for all the medium temperature air coolers. So on one side of that little heat exchanger, we've got the glycol that circulates through the cooler, and on the other side, we have the hot water, and then some valves so that we can, during defrost, generate a closed circuit of warm glycol through the cooler so the ice falls off. And the third use is regeneration of desiccant dryers. Desiccant dryers are used in large freezer applications to prevent slippery floors. Slippery floors are dangerous. When people fall over, they lodge a workers' compensation claim, and that's what we're trying to avoid. So the regeneration of a desiccant dryer happens by pumping warm air of 60 to 70 degrees through a corner of the desiccant wheel to drive the moisture out. So the warm air is heated with the hot water that comes from the desuperheater. And this is significant. In a 40 to 50,000 cubic metre cold store, an electrically regenerated desiccant dryer can consume up to 10% of the electricity consumption of the refrigeration plant that runs that cold store. So this is quite significant. I mean, a typical 40,000 cubic metre cold store with a low charge ammonia plant will take around 1,200 megawatt hours a year. 10% of that is very significant. So the capital cost of this system I showed you on the other picture is about 100,000. That does not include the storage tank. The insulated 316 stainless steel storage tank for the hot water will add another $70,000. So we are saving 245 megawatt hours a year. If that client pays $10 or 100 bucks per megawatt hour, you can work out it's about $25,000 a year. So a payback of about 4 years. On the picture on the right, you see the subfloor heating pipe being laid. It sits below the structural slab, about 30 kilometres of heating pipe in this particular exercise. And just some concluding remarks about reciprocating compressors versus screw compressors. We see discharge gas temperatures in reciprocating compressors from about 80 to 130 degrees, sometimes up to 150 degrees at part load. With screw compressors, it's much less. Oil-injected screw compressors, we see maybe 65 to 85, because a lot of the heat of compression is removed by the oil that's injected between the rotors. We can still recover that heat, but it is at a lower temperature. Typically, the oil temperature in a screw compressor is about maybe 50, 55 degrees entering the compressor, and 70 degrees or so entering the oil cooler. Desiccant dryers are gaining popularity for a whole bunch of reasons. The main reason being the prevention of slippery floors. Other reasons are extending the defrost intervals so that we have more hours between each defrost. Improvement in product quality. We don't have any frost settling down on the product, and quite often the product is barcoded. Frost on the product prevents you from reading the barcode. And large-scale ASRS systems, automatic storage and retrieval systems for boxes, the meat in cartons and the like, they require dew points that are sometimes below -30, because otherwise their automatic retrieval systems simply do not work. So this is an application that's coming more and more. We can also recover all the 88% condenser heat, of course, but that is at a much lower temperature, and it may be a problem finding a use for those lower temperatures unless another high temperature heat pump is added to the system, like Jared was alluding to before. The recoverable amount of heat, of course, varies with the plant load. We try to make part load performance highly efficient because that saves energy on the refrigeration plant. And when the plant reduces in load because it's nighttime or it's a holiday or whatever the case might be, then we need to accommodate that. And this usually happens with storage. So we have hot water storage so we can overcome those periods of low load where we don't recover as much heat as we can at full load. And finally, we can use desuperheaters in all kinds of plants. The peculiarity of ammonia is that it has a high discharge temperature. This is a direct result of the CPCV value. Some people call that the kappa value. It's a ratio between liquid and vapor specific heats. And typically an HFC refrigerant might have a kappa value of 1.2. Therefore, a lower discharge temperature, ammonia is 1.4, and therefore ammonia has one of the highest discharge temperatures of all the refrigerants available for us to use. So thanks a lot for listening. If you would like to ask any questions, feel free.
Absolutely, we've got a couple of minutes for that before we get to Murray. So many thanks for that, Stefan. If I can just throw a one in there first, I heard you say for reciprocating compressor, you've got about 12% of the heat available that's being rejected that you can pick up in the desuperheater. For a screw compressor where you've got a lot more heat goes to the oil, if you were to say add the desuperheating heat and the heat from the oil, is that 12% as well, or where what's the sort of rule of thumb?
Pretty well. Remember that if we recover the heat from the oil cooler, the screw compressor oil cooler, we can probably get no more than 60 degrees out of that, maybe 65. And if we take that same heat and then push it through the desuperheater, well, if you supply a 65 degrees C heat into a desuperheater in an attempt to recover heat in the desuperheater, you cannot cool the discharge gas down below the heat you put into it, right? So in practice, you sometimes end up with two loops. And then you've got to find a use for the low temperature loop, and you've got to find a use for the higher temperature loop that comes out of the desuperheater. Whereas with a desuperheater for a reciprocating compressor plant, well, there's one desuperheater sitting in the main discharge line that is fed by all the reciprocating compressors. So if you're designing a plant from new, well, that's the path you want to follow, because you can get more heat and you can get heat at a higher temperature, and it's simpler and easier to design and install.
Yeah, gotcha. Thanks, Stefan. And just one more. We've got a quick question coming. Let me check that one. 35 degrees is the saturated condensing temperature. Yeah, I think we've got that covered now through there in the chat as well. If I look at one final question there. If you were just preheating some boiler feed water, Stefan, I understand you probably wouldn't need that secondary loop. You know, if that was already softened water without the calcium in there, are you happy for that to go straight through the desuperheater and give you 80 degree water or so?
Yeah, sure. But I mean, I've been caught before where you get told that there isn't anything in the water, and there is, and you end up with a desuperheater that is not cleanable and clogged up on the shell side, and you can throw it away after 6 months.
Off she goes. You got a calcium accumulator.
There are other types of desuperheaters that are cleanable, tube and tube ones, where you have access. You got the water going through the center tube and the ammonia going through the annulus. You can design those things so you can clean the water side with a bottle brush. So, but they're elaborate, not exactly cheap, and it's not something you just go and buy down the road like you buy a plate heat exchanger or a shell and tube.
Good one. We'll put that back to Alpha Laval and ask for someone to develop something for this.
They got something very similar to that. I know they do.
Good one. Stefan, many thanks for joining us this afternoon.
You're welcome.
It's much appreciated.